Hello, this is Math 280, Multivariable Calculus. I'm Professor Wheatley. Today we will begin the final portion of our course, which is actual vector calculus, and we'll start with line integrals. Okay, so you can integrate a function of two variables, f of x, y, over a curve in the xy plane, right? We know we can do it over some region, some box region. You can do it over a particular curve too, right? And you can also integrate a function f of x, y, z over a space curve in space, right? Okay. And if you're doing this, if you're not integrating over a region, but over a particular curve or space curve, what you have is called a line integral. So such integrals over these curves and space curves are called line integrals. Right? And think of them in your mind as really being curve integrals, more appropriate terminology. So curve integrals is more appropriate. Since they needn't be over lines, it can be over any curve you want to be over. And the ideas are going to be the same in the xy plane as they would be in 3 space. So we'll talk about space mostly, but the ideas extend to the xy plane completely analogously. Okay, so let's start here and see what we can come up with. So we start with a function fyz, or f of xyz, excuse me, and a space curve. And we'll say some vector function r of t, which is g of ti plus h of tj plus k of tk between some a and b, right? So there's our space curve defined by the vector function r between some points a and b, okay? So pictorially, we've got some space curve, and it's sitting, so there's z, there's y, so there's our space curve, okay? And the function f, the values of f along this space curve, right, are going to be given by composing f with g of t and h of t and k of t. So for every t value moving along the space curve, you're at some point, x, y, z. Plug those into the function to get f of x, y, z. So values along there are the composition of f with g for x, f with h for y, and f with k for z. And just like when we talked about arc length previously, we don't want different equivalent parameterizations of the same space curve to give us problems, so we're going to integrate with respect to arc length, because arc length remains constant regardless of the parameterization used. Okay, so we'll integrate with respect to arc length. Okay. S. Okay. And our goal is more or less, we're going to actually call this space curve, we're not going to call it r of t, we'll call it capital C, because of the notation down the line uses this, right? And then we're not going to get so very precise with this, but we will cut C up into subarcs, and as soon as we're cutting things into smaller pieces, we think integral and limits and Riemann sums and all that good stuff. And we're going to let delta S be a change in arc length Right? So we're not going to get overly technical here. And so as a consequence, the line integral of a function f of x, y, z over the space curve C, C is written as follows. So we have integral over C, so there's the space curve, f of x, y, z ds, right, with respect to arc length. So that's the notation for the line integral. Okay? Okay, so a couple more details about this. Get rid of that. Alrighty. So recall, we spent a little bit of time on arc length a while back. The arc length s of t from the initial point A to some value t is this expression, right? It's the integral from A to t of the length of the velocity vector v tau d tau. Remember that v is just r prime. And I use that tau because we had a t already up there. So tau is just like a substitute variable. It's nothing to be worried about. But we already have t in the integrand, so we're going to use tau down here as kind of a place-holding variable, just like we did in the arc length section. All right. So we can differentiate with respect to t on both sides. So you take d dt, both sides of this guy, and what you get is you get ds dt, oops, excuse me, ds dt on one side, right? On the other side, FTC tells us that this is absolute value v of t, okay? So as a consequence, you can multiply both sides by dt, and we'll get ds equals length of vt dt, right? So we have an expression for ds in terms of t. Okay, so our line integral, which was f of x, y, z ds over the space curve C, well, we want it in terms of a single variable, so now it's going to be from A to B, right, from the function A to B there, or from the line integral A to B, of f of x, y, z, and then times vt dt as such, and we can even be more explicit about this and really get the t in there, because remember, what is f of x, y, z? It's f of gt, ht, kt, right? So we have f of gt, ht, kt times the length of vt dt, right? And there is an expression for the line integral over the space curve C ranging from t equals a to t equals b entirely in terms of t. Okay? So what do I want to say about this? Let me leave that bottom part up there, and I'll erase this top part. So that's the line integral formula in terms of a single variable. So let's see, where are we here? So the line integral over C is just a single integral of, or single integral, not of, but with respect to t. So with respect to t, right? And furthermore, because we used arc length, as long as we have the curve C, as long as our parameterization of the space curve C equals r of t gti htj, that's a vector arrow, oops, garbage, plus kt k. So as long as C is a smooth parameterization, as long as our parameterization is smooth, right? And that meant that the derivative was continuous and never zero, right? So as long as our space curve has a smooth parameterization, any parameterization will work, right? The below integral, the below formula will compute the line integral correctly regardless of parameterization. It's a mouthful. So all that verbiage says the following, that as long as we give a smooth parameterization of our space curve, in other words, think of a line in space, lots of different parameterizations can be used for that line. Any one of them will work because they're all smooth, and any single parameterization will give you the same value for the line integral. Okay? That's the beauty of using arc length. That's the importance of it. Okay? Okay, so let's try an example of this thing. So we have our formula. We're ready to go with that. What is often the hardest part of these problems is finding a smooth parameterization, but the ones we're going to do are sort of meant to be doable in some sense. So let's integrate the function x minus 3y squared plus z, and let's integrate it over the simplest thing we can think of, which is just a line segment joining 2 points, the first one being 1, 1, 1, and the second one being 2, 0, negative 1. Right? So integrate this function over this line segment joining the points P and Q. Okay? So pictorially, well, let me put the axes up here first. So pictorially, what do we have going on? So there's x, y, and z. X, y, and z. And 2, 0, negative 1 is down there somewhere. 1, 1, 1 is up here. 2, 0, 1. Something like that. So this is the path of integration. So this is the path of integration C. Okay. All right. So we need a parameterization. I'm gonna put an arrow on here. We're going to see that direction of the path makes a difference in some way. It's not a big difference, but I want to consider my parameterization to be traveling from 1, 1, 1 to 2, 0. There should be a negative 1 down there. So I'm going to consider that the path to be following the direction of those arrows there. Okay? So we need a parameterization of this line segment. Well, we know all about how to parameterize line segments, right? We know that we need a parallel vector and a point, right? So the vector PQ, which is 1 and negative 1 and negative 2, right, is the vector traveling from P to Q, right? Traveling from, this is P and that's Q, so traveling that direction. That's the parallel vector. And we can use either point will work. So I'll use P, for example, right? And as a consequence, the equation for my line segment looks like y equals 1 minus t, and then z equals 1 minus 2t. So, and then because I'm deliberately, these are the 2 points that are joining my vector together, the t values here range between 0 and 1. When I plug in 0 here, I get that point. When I plug in 1, I get the point Q. Okay? So this is a smooth parameterization of that line segment. This will work for our R of t, right? So in other words, my curve R of t is 1 plus ti plus 1 minus tj plus 1 minus 2tk, where t is between 0 and 1. So this is our path of integration here. This is our c. Okay? All right. So what else? We also need v, because we need to get the length of v. So what is v in this case? Well, it's I minus j minus 2k. All right. And particularly we need the length of v. We need the length of v, so that should be root 6. Right? Length of v should be root 6. Okay. So now let's compute the integral. So let me come over here and erase. So we want to compute the line integral f of x, y, z ds over the curve c, right? The curve being what I just erased, this path of integration. And let's see here. So the endpoints are 0 to 1 in the t value. Points are 0 to 1. And let's see here. We want f of 1 plus t, 1 minus t, and 1 minus 2t, all times square root of 6 times dt, right? So I plugged in the component functions of r into f, and I multiplied by the length of the velocity vector on the outside, and everything in terms of t. Okay? So let's see what I want. I can pull the root 6 out. So the root 6 will come out front. Get the integral in 0 to 1. When I plug this stuff into f, so let's see here. I plug in 1 plus t for x, 1 minus t for y, and 1 minus 2t for z. So I get what? 1 plus t minus 3 times 1 minus t squared plus 1 minus 2t, and then that whole thing dt, right? So I'm plugging in the component functions for x, y, and z. And you crank that out, what on earth do you get here? So root 6 and 0 to 1, and then let's see, add stuff up. You should get negative 3t squared plus 5t minus 1 is the result of all this junk in here, the algebra there. Okay. So the root 6 is still hanging around out front. Integrating, we get negative x cubed. I'm sorry, negative t cubed. I'm sorry. Negative t cubed. Negative t cubed plus 5 halves t squared minus t evaluated from 0 to 1. Right? And let's see, plug that in, you get negative 1 plus 5 halves minus 1. So that's negative 2 plus 5 halves is a positive 1/2 times root 6 gives you a root 6 over 2 value as your line integral. Okay, so that's the integral of that function over that path. It's worth noting briefly, too, that if we changed the direction of the path, we would have gotten the negative of this thing. If we changed the direction of the path, we would have gotten the negative line integral here. So we would have got negative root 6 over 2 if our vector had been the vector QP. Okay? But any parameterization would have given us either that integral or its opposite, changing the direction of it. Okay? All right. So that wasn't too bad. There are other things that make us even nicer sometimes, though. So it may be that our path is not particularly nice as it is, but if we could break down our path of integration into nice pieces at least, we might be able to do something like that. So the fact is, line integrals have a property. Line integrals have this property called finite, property of what's called finite additivity. Finite additivity. What that means is that if C is made up of a bunch of curves C1, C2 through Cn, and there are finitely many of these, there's not infinitely many of them, there's just some finite number, so a bunch of finite number of curves lined up, and if you lay them out, laid out end to end, and there's no overlap, then the integral over C is equal to the integral over C1 plus the integral over C2 plus dot 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 plus the integral over Cn. Okay? So when you have a finite number of curves, C1 through Cn, making up the curve C, right, you can just add up all the separate line integrals and you would get the actual integral that you want. Okay? So let's try that out here. So, example, evaluate the line integral C of 2x ds, where C is the arc C1 of the parabola y equals x squared from 0, 0 to 1, 0, followed by vertical line here, followed by the vertical line segment C2 from 1, 1 to 1, 2. Okay? So here our curve C is made up of two separate pieces attached end to end. Why is this 1, 0? This should be 1, 1. That looks better. Yeah, there we go. Okay. So, in other words, what does the picture look like? What does the picture look like? Well, so 0, 0 to 1, 1 is that arc, right? So there's the parabolic arc. This is C1, and then we have a line segment which extends up. That's 1, that's 2. We have a line segment going up like that, right? So the order or the path of integration, right, is following this up, heading up that vertical line segment. Okay? Okay. And this is 1, 2, and this is 1, 1. This is curve C2, and this down here, of course, is 0, 0. Okay, so, yeah. Do I want to erase yet? Probably. All right, so there's our picture. Let's get rid of our fact up here. Give ourselves some room to work. In fact, let me cut the whole problem out of here. So we have our picture. We've seen that. We know what it looks like. So now, C1 was that parabolic arc, and that's the graph of a function of x. So we can use any parameter that we want to. We don't need to feel addicted to t. I mean, we can use whatever we want. So this is a function of x. We may as well use x as a parameter. So as a consequence, for that part of the curve, x is just x, right? X is varying, and y is dependent on x, so y equals x squared. And our x is ranging between 0 and 1, right? Because I'll draw it again over here. So there's the curve, there's the vertical line, there's 0, there's 1, right? So x is varying between 0 and 1. Y is changing according to x, okay? And so a smooth parameterization of our curve is just xi plus x squared j, right? So this is smooth parameterization of c, right? xi plus x squared j. Okay. And let's see here. We need the velocity of that. So we have I plus 2xj. And so the length of the velocity, I'm calling this v1 and r1 because it's associated with c1, the first part of the graph. So the velocity here is 1 plus 4x squared in the square root. Okay. So the velocity, the length this time doesn't involve x. Okay. So on the first part of the graph, just the first part, the integral 2x ds. So x is our parameter, so we're going from 0 to 1, our limits of integration, right? We can leave 2x by itself, essentially, and then multiply by the length, right? Square root of 1 plus 4x squared, and then we have dx, okay? So now, how do we want to integrate this? Well, let's see here. We can let u be 1 plus 4x squared. Then du is 8x dx. All right, so there's our 2x and our dx. We like this. So we got to hit it with a quarter. So 1/4 du is equal to 2x dx. Sounds good to me. So this winds up being the integral of what, u to the 1/2 times a quarter, right? So we've got what, we got 1/4 times, actually I guess I don't need the integral symbol anymore, do I? So this is 1/4 times, so that would be the integral of u to the 1/2. So integral u to the 1/2 times a quarter is 2/3 times 1/4 u to the 3/2. Right to me, yeah, that looks good, okay. So this would be 1 plus 4x squared to the 3/2, and then, so I don't need brackets in here. Making this look not as I want it to look. So there's parentheses, parentheses, there's from 0 to 1. So there's the integral, right? So there's the integral. And when we plug in, what do we get? We plug in 1. We get, so the 1/4 and the 2/3 can go outside, so that's just 2/12. It's 1/6. You plug in 1 here, you get 5 to the 3/2. And when you plug in 0 in there, you get just 1 to the 3/2. You get this -1. And let's see, 5 to the 3/2 is the square root of 5 cubed. So that's the square root of 125 minus 1. You could pull out the 25 there, and you get 5 root 5 minus 1. So there is the line integral of that first part. So this is the integral of f over that first part only, C1. Okay? All right, let's try C2. So C2 is a vertical line segment. So everything's good here. Let's erase, and we'll go to the second part of this. So let me leave my picture up. So now I want to address this vertical line segment here between 1, 1 and 1, 2. I want to address this part here. So C2 is a part of the line x equals 1. So we can let y be our parameter here since y is varying and x is staying constant. So as an example, x is 1, our parameterization y equals y, and we're ranging between 1 and 2 on the y-axis, right? So this is 1, 1, this is 1, 2, so we're ranging between 1 and 2 on the y-axis, okay? And so our smooth parameterization, R2 of y, is just I plus yj, and our velocity vector of y is just j, right? And the length of that is certainly 1. Right? So there's our smooth parameterization of that vertical line segment. Okay? So as a consequence, C2 2x ds is from integral from 1 to 2. There's integral from 1 to 2 of 2 dy, right? Since x is equal to 1, right? So we're plugging x equal to 1 here. This is just 2 dy, and the velocity is 1, okay? So this is certainly going to be 2y from 1 to 2, and that's 4 minus 2, which is 2, okay? So that's the integral over that vertical line segment, okay? So at the end of all of this, our whole question was, what's the integral over the entire curve C, which is made up of these two pieces together? Well, we have finite additivity. So it's the sum, right, of those two parts. So this is 1/6 5 root 5 minus 1 plus 2. Right? Okay, and there's your answer. So this comes in handy when we can break down regions into smaller pieces. Okay, let's try one more here to point out an important principle here. So let's see what we got. Let's do another one, but let's evaluate it two different ways here. So let's evaluate integral from C, integral over C of y sine z. And let's do it two separate ways. So first, I want C to be the circular helix R1 of t equals cosine ti plus sine tj plus tk between 0 and 2 pi. So that'll be the first C I'll integrate over, okay, as a circular helix. And then secondly, let's have C be the line segment joining the points 1, 0, 0 to joining 1, 0, 0 to 1, 0 and 2 pi. Okay. So now notice this is not two pieces of one curve, it's two separate paths I'm taking. Okay? So, draw a picture here. Let's see here. What haven't we used in a while? Green. So, the helix, okay, so the helix starts, so when t is 0, that's 1, and that's 0, and that's 0, so it starts at 1, 0, 0. Okay, and it travels in its helical path, so it's going something like that, and then it's sort of coming back around, and then it's, when you plug in 2 pi, that's 1 again, and that's 0, and that's 2 pi. So this is the point 1, 0, 2 pi, right? So we're traveling in the direction of the arrows, okay? And so that is the first curve we're integrating around, is this helix. It's circling around like that, okay? Notice it starts at 1, 0, 0 and ends at 1, 0, 2 pi. So this is A. Okay, well, B also starts at 1, 0, 0 and also ends at 1, 0, 2 pi. But notice it's a lot shorter. I mean, there's a lot less to the path, right? So these are both, and we're going in this direction, right? So we're going that direction, we're going that direction. They both have the same starting and ending points, but different paths for getting there. So we might expect that in this case, we're going to get different line integrals. That's just what we're going to have happen. All right, so let's look at these together. So let me erase the pictures and the descriptions. We know what our regions look like now. Let's do the integration. So on the first one, I'll put R1 back up here. It was cosine t plus sine t plus tk. And that means that the velocity vector here is going to be negative sine t plus cosine t plus just k. Okay, so there's the velocity vector. And so the length of that guy is going to be root 2. Okay, it's going to be root 2, the length of him. All right, and let's see here. So our integral c1 y sine z ds. So our time interval is 0 to 2 pi here, all right? We're going off of t being our parameter, so y is sine t, and sine of z, so z is just t, so we really have sine t times root 2 dt, right? So I plugged in for y, I plugged in for z, and I put my length of v of t over here, okay? So I can yank that root 2 out, integral 0 to 2 pi sine squared t dt, right? Now we can use one of those arcane trig identities we love. So it's 1/2 1 minus what, cosine 2t. That'll do the trick. That'll get rid of the squared to give us a sine squared, something easier. Okay. So again, if something doesn't look good and it involves a trig formula inside the integral, it may very well be that an identity can save the day here. So take a look around at those. So this is 1/2 1 minus cos 2t dt. Okay, and I can pull the 1/2 out. That's no problem. Integral from 0 to 2 pi of 1 minus cos 2t dt. Okay, and let's see here. So what do we get? We get pi over 2. The 1 becomes just a t. Cosine 2t is what? Minus 1/2 sine 2t is the integral of that. Does that work? Yeah, it does. It does. Yes, that's reverse chain rule there. And we're integrating over 0 to 2 pi. Okay. So let's see here. When I plug in 2 pi, I got a 2 pi here. That's gone. When I plug in 0, the whole thing zeroes out. So I wind up actually with root 2 over 2 times a 2 pi, which is just root 2 pi. All right. So that is the value of the integral over this particular path. Okay? All right. So that's the first curve. That's C1, the helix. So notice its value was 2 pi. Let's try it over the second curve, which was that vertical line segment. So let's try it over the second curve, which was the vertical line segment. All right, so now B. So now we had a parameterization. So we have to parameterize. That's from 1, 0, 0 to 1, 0, 2 pi, right? So the parameterization there, right? So the parallel vector is something like 0, 0, 2 pi. Oops, that should be a vector. And we could use any of the points, so this point will work. So our parameterization is something like plus 2 pi tk, right? So there's the smooth parameterization of that line segment, okay? And let's see, so the V2 there, and this should really be of t, there, of t, okay? So this is V2 of t, is just 2 pi k, and the length of that is certainly 2 pi, right? That makes sense, okay? So the integral of C2 of y sine z ds, well, notice that in the parameterization, y is 0, and sine 2 pi is also 0. So this whole thing is just 0. It's just the integral C2 0 ds. that means the value of the integral is 0, right? So clearly this is not equal to root 2 pi. So we saw that what we ended up here was two different values of a line integral, even though the ending and starting points were the same, but the path taken was different, right? So though both C1 and C2 shared common endpoints, the line integral of f changed. Right? So the integral of f changed from C1 to C2. It wasn't the same. Right? And so that's true in general. So in general, line integral depends on path, not just endpoints. Okay? And we'll see in I guess it's 2 sections from now, if we can find functions that this doesn't matter for, so-called path-independent functions, then we have very nice properties that stem from them. But for us, for right now, most functions do in fact, the integration does in fact depend on the path taken, not just the endpoints. Okay, that's it for line integrals.